Alright, so what I'm going to go over in this short video is going to be about ANOVAs and their types of math. So, been teaching this class in R for the first time this semester and been learning the tricks of the trade, so to speak. And I had a student come and talk to me about my advisor and I are getting different ANOVA results. And so exploring this idea of the different types of sum of squares a little more thoroughly in R so we can understand what's going on. So this is how to ANOVA in R, like your advisor who's using SPSS. So the big problem is there are several different mathematical forms of ANOVA. Most of psychology has adopted what we would call type 3. And I really think that's partially because that's what SPSS does automatically. And so a lot of the reasons why we do things are originally based on theory. Type 3 is probably the best if you're interested in interactions, but have been sort of lost to the fact that this is the way the program does it, and that's all I know. It's not really obvious what type R is doing for you, so hopefully this will clarify a little bit about what's going on and when you'll see it acting up and when you won't, which is part of the problem we've been having this semester. So a quick explanation of the math that doesn't involve a whole lot of math. There's 4 or 5 different types of sum of squares, but I'm going to just talk about the big 3. So type 1 is called sequential sum of squares, where what happens is the first IV in your equation gets tested first. Then you add in IV2, given that IV1 is already accounted for, and then you add the interaction, given IV1 and 2. It's very similar to a hierarchical regression. And so if you think about this, in my example using classes, the variance is a jar of cookies. IV1 gets to take as many as it wants first, then IV2 takes as many as it wants second, and then the interaction gets whatever is left over. So the order of the IVs matters. Depending on which way you write it matters. Type 2 actually assumes that there's no significant interaction. So it's similar to a simultaneous regression. It's that it's test IV1 given that type IV2 is there. Test IV2 given that IV1 is there. So they're both grabbing from the cookie jar at once. And this will give you more power if the interaction is significant. But in general, I would think that if you were interested in this type of design, you might do this as regression, because often we're most interested in the interaction. So if you're only wanting main effects, I guess you could do type 2, but often the design of the study is so we can get the interaction between the two IVs. So I don't know how useful type 2 is, given that it assumes no interaction. So type 3 is the most common, that's what we usually use. And it's essentially like all 3 of them are going for cookies at once. So you test for IV1, given that the other things are there. Test for IV2, given that the other things are there. Test for the interaction, given that the other things are there. And that's exactly how a simultaneous regression works as well. So it looks for how much variance is accounted for by this IV, given that the other ones are still in the room. And so what I did was I ran these in SPSS, and I'll click through and show you here how I did that. So I have a very messy data set, and this is the key to the issue. So let me just show you real quick what the issue actually is. So I have some messy data from our lab. This is not something we're analyzing, so I figured I could show it to you guys, where a student's interested in English as a second language. And so we asked people, is English your first language? And then we also asked for their gender. And so if I'm looking at the condition ends, so how many people are in each group, it's very uneven. Because it's sort of hard to get guys to participate in studies, and it's also sort of hard to get non-English speakers as well here. So we have actually this is the non-English speakers. These were our freshmen that didn't fill out the study correctly. But either way, very unbalanced N. Everything that we've been doing in class is made of data, so the ends are perfectly even, which is in real research never happens unless you force it to happen. And so the real problem that you'll see where these types give you different answers is with unbalanced N. And so when I was testing this for my class, when we had a bit of confusion about why we were getting different answers, it was partially due to the fact that I was testing it with balanced n. So I wasn't seeing the difference that is there. I was like, R isn't doing type 1 sum of squares. It doesn't make any sense what's going on. But if you take the n and make them different across conditions, the problem becomes a lot clearer. So I've picked some super messy data so that we could see what the actual issue is with the output. It's not really an issue, but just to show you what's going on. So to run this in SPSS is kind of a bit of a trick. So it's general linear model, univariate. I put my two IVs in fixed factors and my DV in dependent variable, but to get something other than type 3 sum of squares automatically, what you do is you click on model. Okay. And let me reset this real quick. Okay. And so I have my two factors over here. So I clicked on both of them, clicked main effects, moved them over. And then I click on both of them and click interaction and move it over. So now I'm getting question 2, question 6, and question 2 by 6. Okay. Down here I changed it to type 1. And so that gives me this output I have over here in PowerPoint. And so you'll see that if I was to look at this, I would look across here, and my question 2 is not significant, question 6 is significant, and the interaction is not. Okay? So easy enough. However, if I then decide to change that order, all I'm going to do is say, you know what, I actually wanted question 6 to go first. So I've just flipped these two. Continue and OK. You should get this output. And so now question 6 is still significant, but question 2 is a very different p-value. Okay? The interaction will always be the same because it goes last. And so just a simple difference between these two analyses is kind of confusing because, you know, why should I get different answers given the different order? Well, that's because type 1 is running, you know, IV1 gets to go first and nobody else is there. Okay? If you switch to type 2, you'll get the same answer as type 1 with the other order, with the second order, even though I flipped them back originally. So I get the same numbers as one of the last ones, and that's because it's testing just those two main effects. It tests the interaction and the main effects all kind of at the same time because you have the interaction in there. If I really wanted to do type 2, I would take that interaction out completely. But I don't really want to do that, so I left it in for purposes of this demo. And then to run type 2, sorry, escape, here we go. In SPSS, all you do is switch model type. Okay. And since so for type 2, what I'll get is the same numbers as if I had run this as type 1 with question 6 first. So I think it kind of is like the largest one gets to go first, I think is what it's doing. But since I have that interaction and it's non-significant, I really should test this without the interaction at all. Right. So type 3 is your normal type for SPSS, so this is just the normal run, like if I didn't click model at all. And you'll see the numbers again, the p-values are different. So it's 0.007 and 0.75 instead of 0.6. And so it's what's really happening is F is changing. But the easiest way to look at it is compare p-values. So here's kind of a summary. So if I do type 1 and put question 2 in first, I get this set of p-values. If I do question 6 first, I get a different set. If I do type 2, I get the same set as question 6. If I do type 3, I get a totally different set of numbers. And so knowing which type you want to do is super important. Generally, people like type 3 because we're interested in the interaction, and we're going to test that simultaneously. So that would be what I would get if I did SPSS. Now, this assumes you know a little bit of R, but one of the things you can do is the AOV function, which is ANOVA, and then you take a summary of the output. So for a one-way design, this works great. It works perfectly. However, if you're going to do a multi-way design and the N are unbalanced, this does not work great. the inner balanced, it looks like type 3. And you kind of just go, what the hell is everybody talking about? Shrug. And then when you have a student go, hey, I don't understand what's going wrong, you go, oh, maybe I need to figure this out. So that's why we're here. So what I want to do is go over here to R. So I loaded up that same data set and set it up appropriately. So I'm going to run this with the AOV function and save it. So I've got verbs. So my DV is approximately question 2 plus question 6 plus question 2 times 6. You don't have to quite specify it that detailed. I could just do question 2 times 6, but this makes it a little clearer what's going on. So I'm going to run that. And when I get, although it's really tiny, is with question 2 first, I get my p-values from SPSS. Okay, so I get the same ones that I found here. Okay, so I get those numbers. If I then switch to putting question 6 first, I get the same ones that I got from SPSS, so I'm assuming I'm doing this correctly. And the p-values change. So AOV plus summary does do type 1 sum of squares, but the only time you'll notice, so far in my understanding of this, is if in or unbalanced. So what should I do? Because often you want to get the same numbers as other people in your field, or they're going to think you're doing something wrong. So the first option is the ANOVA function. It's in the car library. So it'll let me specify which type I want. So what I did was I loaded up, oh here, I tested it so you can see I get different numbers. Load up the car library and I just tell this to run. And this is actually what I was trying to teach in my class. But if you look at the numbers for type 3, now the numbers for type 2 match perfectly. It's quite beautiful. Okay. But the numbers for type 3 don't match at all. They don't match the SPSS output. Don't really know. They don't match any of type 1. They don't match type 2. What the heck is going on? Okay. What's happening is that AOV function and the ANOVA function in CAR are still just special types of regression. And since this is regression, it assumes the order of your factors matters. And this becomes really important if you have more than 2 levels. So it assumes that factor 1 is ordered to factor 2, like if you're doing a dosage study, so no milligrams to 3 milligrams to 6 milligrams, that sort of thing, that's an ordered factor. Our factors are not ordered, right? We have gender and do you speak English as your first language. So those are not ordered factors. And so you have to convince R to do the type of ordered factors that are default for type 3 in SPSS and sort of the way we teach type 3 sum of squares. Okay. So the way to fix that is to use this options command. It goes on its own separate line and then run your ANOVA. And it's typed just like I have it in my notes here. So this options command, then I'm going to rerun that ANOVA. My summary doesn't change because this is type 1, so it doesn't matter. But my ANOVA does change. So I have now switched to the same type 3 p-values that we got before. And so that options contrast, back up, contrast sum and contrast poly set this up to be the traditional divvy up of variance for type 3 sum of squares without getting too much into the math. But that will match anything that someone runs with the exact same data in SPSS. Now, that being said, there is actually a simpler solution that I will totally teach next year and just ditch this AOV function, but is the easy package. Okay, so there's a function called easyANOVA, which is nice. It's easy to remember. The only extra consideration is that easyANOVA requires a participant number. So when you're setting up your data to run, you have to have a participant number, even if it's all between subjects. So easyANOVA is a really great package for running repeated measures designs and mixed designs because it'll do Mockley's test for you, and it just is easier than running an LME. if you want to stick with the traditional ANOVA route. So what you do is you do data equals data, tell it the data set name. Within subject's ID is the participant number, whatever you've called that. Your DV equals. You DV between equals, and I have this dot and these two things. So this is if you want multiple IVs, and you just list them out. So you could put 10 here if you wanted. Detailed equals true, type equals 3. If you wanted repeated measures data, you would add one more component within equals. And so you'd write it just like this line, but the word would be within. Okay? Or if you wanted a mixed design, you could add both. Okay? And so the cool thing about the easy output, although I turned off scientific notation so it gave me 8 bazillion decimal points, is it will do type 3. So if you look at this column, this is type 3 sum of squares. But the reason I might bias you towards using easy, so let me run it real quick, is 2 reasons. First, it tells me unbalanced equal n per group. Make sure you've specified a well-considered value for type. So I could change this to 1, 2, 3 without having to think about, do I need to do the contrast command? Do I need to run this? Do I need to do that? Do I need to make sure my factor's in the right order? You literally can just change it to type 1. It's still going to give me the warning. But then now it says it's highly questionable. Like, are you really sure you wanted to do it that way? But look, we got the same output. Hopefully you're doing this for demonstration purposes only. So it kind of gives you a warning that you shouldn't do it that way. Okay. If I run it as type 2, I'll get those same effects that we saw a minute ago. And then now I can switch to type 3. And so when I run type 3, it still gives me the warning, but I knew that's what I wanted to do, so it gives me F. Here are my p-values, albeit they're very long. And actually gives you generalized eta square as well, which is very similar to regular partial eta square, but not quite. And then it also gives you Levine's. So not only does it give you some of the traditional tests for assumptions, it sort of tells you, are you sure you want to do it this way? So I like easyANOVA now that I've learned it a little better, especially because it's pretty clear what's going on, and then you don't have to remember, okay, I've got to run this AOV, and then I have to do this, and then I have to do this. Kind of set up here. The only problem with easyANOVA is if you want to use some of the post hoc tests that come with the agriculture library, then you will not be able to, because they are tied to using the AOV function. Alright, but that, summary-wise, even if you didn't understand all the little different pieces, is how you can make R and SPSS have the same output.